There's another product pitch on my innovation research on generating electricity.
Okay, I'm back. Can you generate engineering designs for a massive electric generator power plant using static electric discharge? An example is when a person walks across carpet, they build up electric charge. Please detail the best design, materials, heat, fire resistant, etc. Your request for a massive power plant based on static discharge is a fascinating engineering challenge. While the core concept faces significant physics and energy density limitations, designing such a system involves advanced materials, specialized generators, and rigorous safety protocols. High voltage, the core challenge. Physics versus practical power. The fundamental hurdle is energy scale. Static electricity operates at extremely high voltage but vanishingly low current, microamps to milliamps. While human-scale static shocks can reach 30,000 volts, the total energy is minuscule. To generate meaningful power, megawatts, you would need to create and collect billions of these tiny discharges every second, which is currently beyond practical engineering. Energy density comparison. Static discharge conceptual plant, extremely low. Power density, approximately 0.0010.01 W per cubic meter estimated. Key limitation, physics of charge separation and collection. Solar farm, moderate. Power density, approximately 5 to 20 W per square meter. Key limitation, weather, daylight hours. Natural gas power plant, very high. Power density, tilde 501,000 W per cubic meter. Key limitation, fuel supply, emissions. Tornado key design components. A theoretical plant would focus on maximizing charge generation and controlled collection. Charge generation core. Method, triboelectric effect, friction contact separation. Scale-up design, massive, continuously rotating belts or drums covered in specialized dielectric materials, pressing against dissimilar materials. Environmental control, low humidity, less than 30% RH, sealed chambers are critical, as moisture dissipates charge. Energy collection and conversion. Primary collectors, arrays of sharp, conductive points. Corona discharge collectors are fine conductive meshes placed near the charge surfaces. Storage stage, high voltage capacitor banks store the intermittent, pulse DC energy. Power conditioning, a multi-stage system. Voltage reducers, high-frequency inverters would be needed to transform the ultra-high voltage DC into grid-compatible AC power. Building construction materials and fire heat resistance. Given the high voltages and risk of sparks, material selection is critical for safety and function. Generator and structure materials. Belts, drums, high-purity silicone, PTFE, Teflon, are specialized polymers with strong triboelectric properties and temperature resistance greater than 200 degrees Celsius. Friction materials, materials like rabbit fur, specialized textiles, are composite coating selected from the triboelectric series. Support structure and housing, static dissipative plastics, composites, surface resistivity, 10 to the power of 6 to 10 to the power of 9 ohms. These allow controlled charge bleed off, preventing dangerous buildups on the housing itself. For high heat zones, ceramic composites or nickel alloy enclosures would be necessary. Safety critical materials. Conduits and wiring, type 316 stainless steel conduit for all high voltage paths. It offers corrosion resistance, mechanical strength, and can handle high temperatures. Insulation and seals, fluoropolymers PFA, ETFE, and polyetherketone PEEK for wires and seals, with stability up to 250 degrees Celsius and excellent chemical radiation resistance. Spark containment, critical junctions housed in ceramic, e.g., alumina or molybdenum alloy chambers capable of withstanding instantaneous spark temperatures. Shield integrated safety and containment system. Given the extreme fire and explosion risk from sparks in a charge-rich environment, safety is the primary design driver. Atmosphere control, flood key generation and collection volumes with an inert gas, e.g., nitrogen, argon, to eliminate oxygen and prevent ignition. Comprehensive grounding bonding, a mesh of copper grounding plates under the entire facility, with all equipment bonded with a resistance path to earth of less than 1 megohm, ideally less than 10 ohms. Special paint piercing clamps ensure metal-to-metal contact on coated equipment. Explosion containment, the core generation modules must be housed in blast-resistant, thermally shielded compartments with directed venting to a safe area. Continuous monitoring, distributed fiber optic temperature sensors and continuous air particle flammable vapor monitors would be required throughout. Light bulb realistic applications and alternatives. While a grid-scale plant isn't feasible, the engineering principles have valuable, smaller-scale applications. Precision industrial coating, using static to attract paint or powder to grounded objects is a mature, efficient technology that requires rigorous grounding safety. Air filtration electrostatic precipitators used in coal plants and factories, these charge particles and collect them on plates, a form of large-scale static power application for pollution control. Specialized research and testing, electrostatic discharge ESD simulators generate precise static discharges to test electronics, built with the components power supply, HV circuit, capacitors, control system you'd find in a scaled-up plant. Niche energy harvesting, research explores harvesting static from machinery vibration or fabric movement for micro-powering sensors, not bulk generation. Alternative 4, static-like, renewable energy, for a truly massive, weather-dependent energy source within, electrical atmosphere, feel, atmospheric electrical discharge lightning harvesting as a related concept. It faces even greater challenges due to its unpredictable and destructive nature, but research into charged aerosol-induced ionization for guided, smaller discharges is an active field. Microscope next steps for research. If you're interested in exploring the boundaries of this technology, I recommend focusing on 1. Triboelectric nanogenerators TENGs. This is cutting-edge research for micro-scale energy harvesting from motion and vibration. 2. Advanced dielectric materials. Research into composites that maximize charge separation efficiency. 3. High voltage, low current power conditioning. The electronics to handle this unique power profile or a specialized field. Would you like a deeper dive into the engineering schematics for any of the subsystems, like the inert atmosphere containment or the high voltage capacitor bank design?
That's my other video. Anybody's watching this under a non-disclosure contract. Anybody's interested, provide me with financial compensation on this. That's my email.